Today's lesson is operations with radicals. Really what we're looking at is these radical expressions that we started talking about yesterday and what we're allowed to do with them. How can we combine them? How can we, simplify them? Those kinds of things, okay? And a lot of this you've already done or done something similar to it. We're just going to kind of formalize it today. So, like, for example, this first section, products of radicals, we're talking about multiplication here. You have already been doing this. Here's what this kind of relies on, the whole idea of multiplying radicals together. If you have a square root, or any root, really, I guess I'll put an n out there to show it could be any root, and you have like something times something inside of here, you're allowed to separate these and do a root of each one, because roots are all about multiplication. Okay, so we could make this like square root of m times square root of n. You're allowed to separate it like that. And vice versa. I guess I should have made my arrow go both ways. Okay, that you can take two things like this and put them back together again by just multiplying the two numbers underneath here, as long as that n value is the same. You do have to have the same n value here. So, like an example of what I'm talking about here is when I would ask you to simplify, for example, the square root of 50, this is what you did, and you maybe didn't realize that this was what you were doing, but you were thinking about that 50 as, well, that's like 25 times 2, right? 50 is the same as 25 times 2, and then we were separating it, and we were making it square root of 25 times square root of 2. And then we could make that square root of 25 into a 5, and we could just call this 5 square root of 2. So we've already done that, all right? You guys have seen that before. We were kind of going the opposite way of what we're about to do. We were taking something apart. We took that 50, we broke it into pieces, and then we just assumed it was okay for us to take a square root of each one of those separately. Now I'm telling you it actually is okay, okay? We're kind of just formalizing something that we've just sort of taken for granted before. So, like in this first one, if I'm multiplying square root of 3 times square root of 5, I can put those together by just multiplying this 3 and the 5 together, and this would become square root of 15. Okay, we're allowed to do that with multiplication. Okay? With the next example, they're both fifth roots. I do have to check and make sure these two things are the same. Okay, but because they are, now I'm just multiplying these two things together. So I'm going to go 7 times 12, and this is going to give me another fifth root. Notice that the root doesn't change. Just like up here, a square root and a square root still stayed a square root. Now I've got fifth root and fifth root, still a fifth root. 7 times 12 is 84. Okay. Altogether, I would have x to the third, y to the third. And that would be my final answer there. Okay. One thing that I do want to point out here quick is this does not work for addition. So for example, if I tell you to do the square root of 16 plus 9, okay, that is not the same thing as square root of 16 plus square root of 9, okay? You're not allowed to take those apart that way. This does not work when it's addition, okay? You cannot separate it. Because if you think about this, 16 plus 9 is 25, right? So this is really square root of 25, which is 5. And then over here, if I do them separately, square root of 16 is 4, square root of 9 is 3. Well, 4 plus 3 does not make 5, okay? So my point here is this whole like combining the things underneath the radicals and taking them back apart only works if you're dealing with multiplication. It does not work when you're dealing with addition. Okay? Okay, so simplifying radicals, onto that. And I pointed out there's going to be two methods here. Really, there's one method and then kind of a shortcut for that same method. And one of them you already know. It's what we just did. It was this thing up here. So we've done this before with square roots, right? We've said, okay, the square root of 500. I'm going to think about this as square root of 100 times square root of 5, right? Because I can separate that. And then I'm going to make this square root of 100 a 10, and then this square root of 5 would stay under there because it doesn't have any other perfect squares in it. And that's how I would simplify that. Now I'm going to deal with these in just a second, okay? But that's really what I'm looking for here, okay, as far as simplifying. If I wanted to do that over here with this one, I would have to think of a number that goes into 40 that is a perfect cube. So perfect squares we got really good at, right? 25, 36, 49, and so on. Perfect cubes are going to be a little bit harder, right? Do you know 2 cubed and 3 cubed and 4 cubed off the top of your head? So this method that we're using here is sort of a shortcut, and it breaks down a little bit when I go to try to use like a cube root or a fourth root. I mean, if I asked you to do this with a sixth root, do you know all the powers of 6 off the top of your head? Probably not, okay? So what I would do from here is I would take this 40 and I would make a factor tree. So just any two things that multiply to make 40. So I'm going to go 4 and 10, and then this is 2 and 2, 2 and 5. Okay, so I broke it down into its prime factors. Okay? Because this is a cube root, I am now looking for a group of 3 of the same number. So see here that I have 3 2's. Okay? That's going to allow me to put 1 2 on the outside of the radical. So I'm going to have my cube root still standing over here. Okay? And then I've got this lonely 5 here that didn't quite make it into a group of 3 of anything. That guy is going to go back down inside here. Okay, so this was me pulling out. Now, really what this represents, 2 times 2 times 2 is 8, right? 8 is a perfect cube. And then I found the cube root of 8, which is 2. Okay? So that's really where that comes from. But that's what I would do with any of these problems that aren't just square roots. And really, you could do it with the square roots also. Like if you couldn't come up with 105, go ahead and do a factor tree for 500. But this should be a quicker way for you. Okay? All right, now let's talk about those variables. And I'm going to start with this one, and then we're just going to go back and do this one the exact same way. If I have x to the 5th, if I were to make a quote-unquote factor tree for x to the 5th, it would look something like this. Okay? And again, I'm looking for groups of 3 here. So I see one group of 3, right? And that means I can put 1x on the outside, representing that one group of 3 here. Okay? I have 2 x's that didn't make it into a group of 3. Those are going to go back inside the radical. Those didn't make it out of the prison cell here. So x times x is x squared, and that's going to go inside there. So when I go to do the y, that's really like y times y. I can't make a group of 3 out of that, right? So because I don't have a group of 3, I can't put any more on the outside here. Both of these are just going to have to go back on the inside. And so I'll have y squared here. Okay? And so then this whole thing right here would be my final answer. 2x and then a cube root of 5x squared y squared. So going back over here, I'm going to try to talk through this one without necessarily having to write it out, because I don't think you have to write it out every single time. Okay? We already know that we have, from what we did before, we have a 10 on the outside of our radical, and we have a 5 still sitting on the inside of our square root here. This is a square root, so it's really looking for groups of 2. So if I have m to the 5th, we want to think about how many groups of 2 could we make out of that. And if you lined up 5 m's, you could make 2 groups of 2. So I'm putting an m squared here to represent that I can pull out 2. Okay? Now, if I use 2 groups of 2 out of that 5, I would have 1 left over. So that 1 leftover goes back on the inside. So the inside is always like all your leftovers. Okay? So then for n to the 4th, how many groups of 2 could I make? I can make 2 groups of 2. And so I'm going to get an n squared here. How many do I have left over? None. Okay? And so then this thing right here would be my final answer. So that's what it means when it says to simplify. Okay? Simplifying means you're not putting it in a calculator, you're not getting like a decimal answer, you're not making fraction exponents, you're pulling out what you can and leaving behind the rest. Okay, so let's try that with this next one. Whoops, sorry about that. With example 2 here, we are simplifying this thing. Sorry about that. And so my suggestion to you is that we start with a factor tree, okay? Because I don't know all my powers of 5 off the top of my head, and even if I did, I don't know which ones go into 128, okay? So I'm going to split this thing up. I'm going to divide by 2 and make this 2 and 64, and this is 2 and 32, 2 and 16, 2 and 8, 2, whoops, got really down here. Let's see, I'm going to go this way. 2 and 4, and then 2 and 2. Sorry, I had to make mine kind of sideways there. So really, no matter how you made your factor tree, you should have ended up with 1, 2, 3, 4, 5, 6, 7 2's. Okay, 2 to the 7th power is 128, so that makes sense. And what I'm looking for is a group of 5. So I'm going to circle 1, 2, 3, 4. Well, here's 4 and then 1 make 5. I don't really mean to be circling that 8, but there we go. It's kind of a ridiculous way. But so 1, 2, 3, 4, 5 2's. Okay? And so I'm going to put, to represent those 5 2's, I'm putting 1, no, sorry. I'm putting 1 2 on the outside. Okay? To represent that I had a perfect set of 5 there. Here's my 5th root standing over here. I've got 2 leftovers, so I'm going to do 2 squared on the inside. Okay, I'm going to make that a 4 in just a second, but I just wanted to show you that I'm putting 2 2's back on the inside. Okay, G to the 11th. If you need to write it out, go ahead and do it. If not, don't worry about it. But if you had 11 G's sitting there, there they are. We're looking for groups of 5, so I can make one group of 5, and that lets me pull out 1, and another group of 5 is here, so that lets me pull out another. 1 leftover goes here on the inside. So let me clean my answer up here a little bit, okay? This right here, I'm going to make into a 2G squared, and then I'm going to have a 5th root of 4G. And this whole thing together would be my final answer. Really, this is like multiplication in between here. Okay? Okay. One more thing to cover. Quotients. Okay? Meaning division. That's what we're looking at now. Sorry, I shouldn't have printed this back to back. Sorry, you can see all my writing through there. Quotients, really what we want to talk about here is rationalizing. And you've actually already done some rationalizing. To rationalize means to get rid of roots. Okay. I think as far as a literal definition, rationalize means make rational. Okay, make something rational. And most of our roots, square roots, cube roots, whatever, most of our roots are not going to come out to be rational, okay? The problem is, the reason we have to rationalize sometimes is we can't have square roots down on the bottoms of things. It's fine up on the top. We don't want them on the bottoms. You've already done a little bit of this when we worked with I, but what I'm going to do here is if this is a square root of 7, I want to think about what I could multiply that by to get like a whole number back. And so I have a lot of people who say I'm going to square the top and square the bottom. The problem is that changes the value of your fraction. But you're on the right track if you're thinking square. Instead of squaring it, I'm going to multiply by itself. I'm going to multiply by a square root of 7. Okay? That just means that up on the top, I also have to multiply by a square root of 7. And I'm allowed to do that because really what I'm multiplying by now is a 1. Okay? Because this over this is equal to 1. So up on the top now, I'm going to just write this as 5 square root of 7. On the bottom, when I multiply square root of 7 by square root of 7, that gives me just a 7. And this is considered to be rationalized because it does not have a square root on the bottom. The only other thing you can sometimes do with these is if these were two numbers that could be reduced, the 5 and the 7, you could go ahead and do that. So if this was like a 14, 14 over 7 would make a 2, okay? in this case, you can't really do anything. This is just your final answer. Okay? But if these numbers out here could reduce somehow, go ahead and do it. Okay? We actually don't need to worry about this last example. We kind of took that off of there a while ago. So really, this is what you need to be able to do in terms of rationalizing, is multiply by a root, top and bottom. Okay? Okay, that's really it for today. Homework is Lesson Masters 8.5 and 8.6b. I think when you get there, though, you'll realize that I actually crossed off quite a bit on both of them because we're really just doing a couple of different topics out of these sections. It's not the entire section. So not a ton for you to do for homework tonight, but give it a try, and then we will talk about all of this in class on Friday.